A sports car is advertised to be able to stop in a distance of 50 meters from a speed of 90 kilometers per hour. Right? What is its acceleration in meters per second squared? B, how many G's is this? Now, 1 G is equal to 9.8 meters per second squared. All right, so for those of you who are like fighter pilots, are you anyone fighter pilot here? Nobody? Oh, okay. Weekend fighter pilots. When you make like a bank turn or evasive maneuver, or if you ride in a roller coaster, you. Oh yeah, I should do that, huh? Yeah, thanks. Yeah, yeah. We were just gonna have fun here, weren't we? Darn, they found us. All right. We will. Here we go. What? Can you see us? Can you see the screen? Andrew, can you see it? I don't know. Jack, can you see it? They can't hear us. All right, thank you. So this G 9.8 is basically is how much that you would feel in your weight. So 1 G is basically same as your weight. Okay. So we'll talk about that more later on. So let's take a look at this and find out what's given to us. Okay. A sports car is advertised to be able to stop. So that tells us it's going to stop eventually at final. So that's my V final. Okay. At distance of 50 meters. So that's my change in position. From speed of, from this much. That's my initial. And they're looking for acceleration in meters per second squared. So they're looking for acceleration. So let's write down everything we know. Well, initially, we were traveling at 90 kilometers per hour. And final velocity is 0. And delta x is equal to 50 meters. And they want us to find acceleration in meters per second squared. Well, this does not look kosher right here. 90 kilometers per hour. Everything else is in meters, seconds, and so on, but this is not good. So we may have to change this into meters per second to work everything out correctly with um, units. So here, to change kilometers per hour into meters per second, in 1 hour, there are 3,600 seconds, and in 1 kilometer, there are 1,000 meters. So if you work this thing out, I think you get something like 25 meters per second for 90 kilometers per hour. So it looks like we have 4 variables here, right? And we don't have time variable. Since we don't have time, we can use equation number 3. Equation number 3 states Vf squared is equal to Vi squared plus 2a delta x. So Vf, 0, square that, still get 0. 25, square that, you get 625 plus 2 times a, which is what we're looking for, and delta x is 50. Therefore, 0 is equal to 625 plus 100a. So my a is equal to negative 625 over 100, which comes out to negative 6.25 meters per second squared as my acceleration. Why is it negative? What does that mean? It's slowing down. Good. This is slowing down, okay, going forward, right? Good. Then it asks, how many G's is that? Well, in 1 G, right? In 1G is 9.8 meters per second squared for 1G, right? So if I know I am going at 6.25 meters per second squared, and if I divide that by 9.8 meters per second squared per 1G, we're going to actually get G's, okay? So these meters per second squared should cancel out and give you G's. And this comes out to 0.64 G's. So that's about 64% of your own weight is how much you would feel when you're stopping like that. Yeah. Yeah, G's are just like a magnitude. And we already know you're going to feel that much G's, and that's how it feels. Okay. All right. Good. So, number 3, a car accelerates from 12 meters per second to 25 meters per second in 6 seconds. Wow. In that one sentence, it gives us a lot of information right there. Okay? So it says it accelerates from 12 meters per second to 25 meters per second. So this looks like the initial velocity. So VI is equal to 12 meters per second. My VF looks like 25 meters per second in 6 seconds. So that's my time. What was the acceleration? Boom. So for part A, all we have to do is just use equation number 1, right? So VF is equal to VI plus AT. Boom. Therefore, 25 is equal to 12 plus A times 6.0. So if we solve for A, then A is equal to 25 minus 12 over 6. So A comes out to 2.167 meters per second squared. Okay. Then it asks, how far did it travel in this time? So how far did it travel in this time, assuming it's a constant acceleration? So how far did it travel is really, they're looking for delta x. Okay. So for part B, VI is equal to 12 meters per second. VF is equal to 25 meters per second. T is equal to 6 seconds. And I mean, I have acceleration too, but what if I did this one wrong and use it? I'm double jeopardizing myself. So I'm going to just look for delta x directly from here without using the previous one. I mean, if you want to use this, there are plenty of other ways to solve this other than, right? So for this particular variables, I can use equation number 4, right? Equation number 4 is delta x is equal to VF plus VI over 2 times t. All right. I mean, you could have used equation number 2, 3, or 4 to figure this thing out. All right. So delta x is equal to VF 25 plus VI 12 over 2 times time, which is 6. So delta x, if you work this thing out with your calculators correctly, you should get 111 meters. All right, any questions? Okay. All right. Any questions in the cyber world? All right, good. Let's take a look at the next problem. A car traveling 90 kilometers per hour strikes a tree. That's not a good thing. Usually, tree will win. All right. I swear, Lucifer, I honked the horn. The tree never moved. The front end of the car compresses, and the driver comes to rest after traveling 0.8 meters. What was the average acceleration of the driver during the collision? How many G's is that, right? Basically, it's the second part. So this 90 kilometers per hour, we already know what that is in meters per second, don't we? We already figured it out previous problem to be 25 meters per second, I believe, right? So we know this is 25 meters per second. And that is our initial traveling velocity. When you hit a tree, you're going to come to a rest. So my final velocity is going to be 0. So here's my initial velocity, which is 25 meters per second. And my final velocity is equal to 0. Right? And driver comes to rest after traveling 0.8 meters. So that's 0.8 is my delta x. Okay? So they want you to find what the acceleration is. Well, because I don't have time variable right here, I could probably use my third equation, equation number 3, which is Vf squared is equal to Vi squared, okay, plus 2a delta x, okay? Yeah? This recording, yeah. Yeah, well, you could figure that out actually, Jack. Yeah, I'd say you could figure it out. I'll show you later, Jack. Hold on. Let me go through this problem and I'll show you. That's why we have these different equations, because we don't even need time to figure this out. Okay? So have patience and watch. So here, my final velocity is 0. Square that, and you're still going to get 0. Initial velocity is 25. Square that, you get 625 plus 2 times a times delta x, which is 0.80. So if you work this out, you could get your acceleration directly. 0 is equal to 625 plus, here you get 1.6a. And if you work it out, solve for acceleration, your acceleration comes out to negative 625 over 1.6. And that looks like a huge acceleration of negative 390.6 meters per second squared. So you are decelerating at rate of 390.6 meters per second squared, and that is, right? That is huge G's. Basically, if I were to look at 390.6 divided by 9.8 meters per second squared per 1G, right? I get something like 39.9 G's. You know what that means? That means about 40 of you, right, on top of you. So Hayden, imagine if you're laying down on the ground and 40 of you are laying on top of you. That'd be very uncomfortable, right? So this is probably not survivable. Like, I mean, if even if you live, it's not going to be like you're not gonna you're gonna have some kind of permanent damage. Yeah. Because I just want to know how many weights do you feel. So it doesn't really matter what the direction is, but you know what I mean. I'm just looking for just the magnitude of it. Okay. Well, Jack, let's take a look at what's going to be like. How many seconds it's going to take to slow this? I mean, come to this stop, right? I can actually figure that out if you want, if you use the fourth equation. So if you say delta x is equal to Vf plus Vi over 2 times t, you can figure out how many seconds it's going to take for you to stop. So since your delta x is 0.8 and your Vf is equal to 0 plus 25 over 2 times t. So you could work this thing out. So you're going to get 1.6, right, divided by 25. So that's going to be the time. So your time comes out to 0.064 seconds to stop. And that's why you're going to get hurt. If it takes longer time for you to stop, you're not going to feel as that much force. But this versus that is completely different, you know? So how can we reduce this G's? By looking at this. How can we lower this? What can we do to lower this? Charlie, what would you say? Add more distance. Yeah. If you add more distance, you're going to be dividing it by a bigger number here, so your acceleration is going to go down. Yeah. Yeah, slow the hell down. You know? Slow the heck down. People are just driving way too fast. If you half of this speed, if you drive half as speed as this, right, your G goes down by not half, but 4 times. So if you go instead of 25 meters per second, you go 12.5 meters per second, the G's that you would feel would be only like less than 10. You know? So slow down. So what Charlie said is increase the distance. Yeah, that's also going to be good. That's why, you know, like back in 50s, they used to build cars like tanks. You know, you could drive through brick wall. I don't know why you would, but you could. And the car probably won't get even scratched. But the occupants inside got mangled because they absorbed all the energy. So one car company said, you know what, we really should protect our drivers, right? So they designed the car with a crumple zone, so car becomes like an accordion, absorbing most of the energy as the car crumples. So the occupants can actually just walk away from the accident, right? Yeah. Yeah, in the car. Car absorbs everything, you know? And that's brilliant actually, right? You know which company is the one who started this? Mercedes Benz. Yeah. They're the ones who started it because they want their customer who's paying $120,000 to live so they could go buy another $120,000 car after an accident. Duh. Brilliant, brilliant, I think, right? Yeah. So now that crumple zone is pretty much standardized through all reputable car manufacturers now, right? If you don't have that crumple zone, you cannot import it into the United States or make it in the United States, you know? Then the second kind of, safety feature they have is 3-point seatbelt system, right? Before they only had a lap belt. And when you get into an accident with a lap belt on, you didn't fly out of the car, but your spinal cord got severed, right? Very bad. Mr. Volvo lost his wife in a car accident, right? So he promised he's going to make his car safer. So he and his engineers developed a 3-point over the shoulder, right? 3-point safety belt system. And he didn't even patent it. He said, this should be for every car, and I should not make profit off of this. So everybody uses it without, very cool, I think. Also, like they also have, airbags now to protect you. So you should feel invincible when you're driving. So everybody's driving like mad people, really fast, right? Crazy. So I say, take out the airbags, take out the seatbelts, and put a huge spike coming out of the steering column. So everybody's gonna drive nice and slow. Say, slow down, guys, come on, slow down, please slow down, right? Oh God. I think it makes sense. I don't know. Then again, I'm a physics teacher. What do I know? Just kidding, just kidding. I was only kidding, guys. Okay. Gee, they can't see my face expression. Well, you can't either because I got my mask on. But I was joking. I swear, I was only joking. All right. Next problem is very important problem. All right. Next, this is important. So I'm going to put some stars next to these. So this is important. Ready? A speeding motorist traveling 120 kilometers per hour passes a stationary police officer. Wow. Okay, so that tells me two things. First, that is so annoying. Yeah, close the door. So there are two objects or two agents here, right? One's a motorist, another one is a police officer, right? So we have a mo, and then we have a po. Right? Po is a code word for police in a gangster code. If you're a gangster like me, you would say po. You don't say police, right? That's how you are cool. You know you're cool when you say po. Yo, it comes to po, and then you're like run. All right. So po versus mo. Silly. I like being silly. It's all right. So we have to divide it up into two things, mo and po. Okay. What do we know about mo? Well, this motorist is traveling at 120 kilometers per hour. Okay. And and speeder is going at the constant speed. So initial velocity of the motorist is 120 kilometers per hour. And since this motorist is going at a constant speed, the acceleration of the motorist is zero. Right? That's all we know for the motorist. However, for Poe, he's stationary, which means he's not moving or she is not moving initially, right? This police officer's initial velocity then is zero. Then acceleration of the police happens to be 10 kilometers per hour per second. Now notice the mixed units here. It's not meters per second squared, but it's kilometers per hour per second, which means for every second, this police officer is gaining speed of 10 kilometers per hour. So 2 seconds later, 20 kilometers per hour. 3 seconds later, 30 kilometers per hour, and so on, so on, right? So we know it starts at zero, speeds up. This motorist is just constantly going. So if I had like a diagram like this, here's Po, here's Mo. This is the starting position. As soon as the motorist passes this line, we're going to start this stopwatch. So here, ready? And then we're going to go, right? And then it's going to follow, and then eventually going to catch up. All right? Common mistake people would say is, well, if it's getting at 10 kilometers per hour every second, when he reaches 120 kilometers per hour, shouldn't he get him? So shouldn't it be 12 seconds? And the answer will be no, right? Because the motorist is going and the police follows, and then once he reaches 120, he's going to constantly say, wait, no, wait, stop, no, wait. It's just, you know what I mean? They'll be just, it's not going to work out. But matter of fact, the police has to travel much faster than 120 in order to catch up to it, to be next to that motorist. So how much distance difference is there for the motorist traveling from the starting point to the police traveling from the starting point to where they catch up? How much distance difference is in their distance wise? For the motorist to travel from here to here, and then police, right, follows and then stops. How much difference is there between the two changing positions? Is there any difference in changing position between the motorist and the police? Huh? So here's the police, motorist which one, and as soon as it passes the police, right? The police follows and catches up. So the delta x's, are they different? No, from the starting point, if this is the starting point right here, right? Here's the police. As the motorist travels, we're going to start, as soon as the motorist travels, starting here, start, and then it's going to go like this. Stop. Is there a difference? No. My delta x for the motorist and my delta x for the police is going to be exactly the same distance. Does that make sense? Okay. So I can say my delta x for the motorist is exactly same as my delta x for the police. What about the time? Here's the police, here's the motorist, and then we're going to start. Stop. Huh? Same. So time for the police must be also same for the time for the motorist. Is that good? All right. Therefore, it looks like I have to have two unknowns here. That means I need two equations, right? Systems of linear equations. Therefore, it looks like here I only have four variables that I can use for second equation. Here I only have four variables that I can use for second equation. So I can use second equation for both of these Johns. All right. So here, my delta x for the motorist is equal to VIT plus 1/2 AT squared. Now, for those of you who are using a monochromatic writing utensil, you're going to have to put some subscripts down, right? Like VI mo, right? AMO, XMO, right? And here, my delta x for the PO is equal to VI PO T plus 1/2 A PO T squared. And since we said these two delta x's are equal to each other, right, we can say these are also equal to each other, right? Because we said that, we could say these are also equal to each other. Cool? Then we can eliminate one of the variables, saying that VIT plus 1/2 AT squared is equal to police VIT plus 1/2 AT squared. Now we know acceleration for the motorist is 0. And we also know the initial velocity of the police is 0. So now we can say initial velocity of the motorist, which is 120 kilometers per hour, right, times time, is equal to 1/2 of, right, A, which is 10 kilometers per hour per second times t squared. Now these times are same, right? These times are same times. So I'm going to go with one color now and say, okay, I'm going to bring this to the other side, okay? So 120t is equal to 5t squared. So 0 is equal to, right, 5t squared minus 120t. Let's factor out 5t. Here, then I have t minus, this is 24. So time is equal to either, if I make this t equals 0, it doesn't matter what this is, it's all going to go to 0. Or if I make this 0, it doesn't matter what this is, the whole term is going to go to 0. So it's going to take 24 seconds to catch up to the motorist. And this makes perfect sense, these two times. Why? At 0 seconds, the speeder and the police were right next to each other. And then 24 seconds later, they were right next to each other again. Yeah. Not seconds. Seconds don't cancel out, but the kilometers per hour do. Yeah, this is the acceleration. So this seconds still remain at the bottom here, but it's per second. So when that unit comes out to the other side, that per second turns into second for the 24. So this has a unit of per second. So when you divide that 1 per second, and then you bring this to the other side, becomes positive 24, then unit turns into seconds then. So it does work out. Yeah. So, okay, that was part A. What about part B? Yeah. Because soon as the motorist passes the police, I'm going to start my stopwatch. Right? So, no, ready? Start. Stop. They traveled same amount of distance and same amount of time. You know, because it takes the exact same amount of time to travel that same distance, even though one traveled at a constant speed, other accelerated from 0 to that speed. They still reach the same place, the same amount of time. All right, so part B asks, how fast would the Po be traveling? Well, that's easy now. Now you just plug in this time for the police. So VF is equal to VI plus AT. You're looking for VF. Your VI, you know, is 0 for the police, because it's stationary police. We know the acceleration, which is 10 kilometers per hour per second, right? Times 24 seconds. So notice how the seconds will cancel out nicely, giving us 240 kilometers per hour. That's like 135 miles per hour. So don't try to outrun the cops. They'll get you. Those Crown Victorias can actually book. You know? All right, so how can we represent this visually, graphics-wise? Well, if I were to draw a velocity versus time graph for this situation, okay, so here's my velocity versus time graph. So here's my time, t in seconds, and here's my velocity in kilometers per hour, right? Ew, look at that. That's gross. Look at that. Look at this. Smudged it. I know. Being a teacher is a hard job. All these ink marks everywhere. Looks like I've got a tattoo. I think I'm a gangster. So if I were to represent the velocity of the motorist is traveling at a constant velocity of 120 kilometers per hour. Does that make sense? Right? So if I were to represent this, right? This 120 kilometers per hour is a constant velocity. So the area underneath should represent the delta x of my, right? The PO, however, started at 0 kilometers per hour and accelerated at 10 kilometers per hour per second. So the slope of this is 10 kilometers per hour per second. And they would meet up at It would meet up at 24 seconds later, right? So I should draw this a little bit more, a little bit longer. And guess what? If I find the area of this red triangle, this area of this red triangle should be exactly same as my area of the blue rectangle, because they both represent delta x. Okay? So if I look for the area of this, it should be exact same as the area of that. And that even looks like, because if I chop this off right here and then put it in here, that's going to be exact same area. Okay? Now, let's make this yeah, Charlie?
So what if you add another distance?
This, well, then is you're going to have to draw another graph. You can't put another distance axis on this. You probably can, but that's going to look messy. You could probably do it in computer, yeah. So you could like do like three-dimensional, like you could rotate it this way and then rotate it this way, with the time axis being like a radial axis. I guess you could do that, yeah. But yeah, you can do anything these days because of computers. Computers are just absolutely amazing. All right, to make this more realistic, how can we do this? Well, you know the police is not going to chase the speeder as soon as the speeder passes. Most likely, realistically speaking, as soon as the speeder blows by the police has to put the donut down, put the coffee back in the thing, start the engine, put it in gear, and then floor it, right? So there's going to be a delay, right? So let's say the police, instead of chasing the speeder right after it passes, let's say it chases the speeder about 6 seconds later after the speeder passes by, right? How would that look different on this? Yeah. Yeah, so it's not going to be starting here. It's going to be starting here, and then it's going to be going chasing after the. So most likely, it's going to be somewhere down here, right? Does that make sense? Yeah. Right here. Yeah, This is the time, which is 12 seconds, is when he reaches, right? When he reaches 120 kilometers per hour. When he reaches 120 kilometers per hour, that speed is like way up there still. You know what I mean? So what Charlie said was, can we represent this in position versus time graph? And absolutely, when we do that, you know what it looks like? For the position versus time, the mo should look like this. And the slope of this is 120. Po is going to be one of these Jones. Now they intersect because the position has to be the same. And the time has to be the same. Does that make sense? Okay. And if I were to look at the 6-second one, right? If I were to look at 6-second one, instead of starting at 0, it starts here, and then it's going to do one of these Johns. Is that good? Okay. So the distance is still going to be the same for both, whether it's 6 seconds later or exact same time. The distance they travel are the same for the both motorist and police. Okay. Good. Any other questions? Any questions in the cyber world? They're all snoring. I could hear them. All right. Moving on. Ah, King Kong. So sad. Falls in love with a blonde girl and just trying to protect her and dies. Dies. Tragic. So calculate how long it took King Kong to fall straight down from top of the Empire State Building, 380 meters high. That is so sad. I don't know if I can do this probably. So here, I have my Empire State Building. And my poor King Kong trying to protect the girl he loves, right? Climbs up to the Empire State Building, fighting off those planes, and then eventually falls straight down. That means the initial velocity in y. So King Kong, instead of like jumping up and then like going down like this, try to make it really dramatic. Like, it's not gonna work. Or just like dives down. He actually just like goes, like falls off, right? So the initial velocity in y is 0. So that's a safe assumption. Okay? And he's gonna just go, whoa, right? So we know initial velocity for the King Kong is 0. Here, y final, right? Y final is 0, and my y initial happens to be 380 meters. So my delta y is equal to y final minus y initial. So my delta y is equal to 0 minus 380. So my delta y is equal to negative 380 meters. And then they ask how long it took. Well, how long doesn't mean like length. This means time. How many? They should have wrote down how many seconds does it take, right? That's what they should have said. But that's what happens when you have physicists or physics majors writing these English language problems. So here, let's write down everything we know. Initial velocity is 0. We know delta y is equal to negative 380 meters. Oh my God, that's all we know. Do we know anything else? Yeah. King Kong lives on Earth. So the acceleration in the y direction is g, which is negative 9.8 meters per second squared. Now, this is a good assumption, right? And I'm looking for time t. Okay. So for part A, it asks how many seconds will it take? Looks like I can use second equation here, right? So delta y is equal to v I y t plus 1/2 a sub y t squared. My delta y is negative 380. VIY is 0, so this whole term just drops out, plus 1/2 times negative 9.8 times t squared. So negative 380 is equal to negative 4.9 t squared. So t is equal to, right, square root of 380 divided by 4.9, which comes out to 8.8 seconds. Wow, 8.8 seconds. That's quite a lot. I don't know if that's long enough to like say your prayer. So I don't know. I guess if you're say it fast. Vater unser in Himmel, geheiligt werde dein Name, dein Reich komme, wille geschehe wie in Himmel, so auf Erden. Unser täglich Brot gib uns heute. Yeah, it's not going to take it. It's going to take longer than 8 seconds, I think. Anyway, yeah, that was German. All right, here we go. What about part B? His velocity just before landing. Right? We're not talking about when he hits the floor, dust goes up, and then it settles down. We're talking about just before the first hair of King Kong touches, right, the first atom of the concrete. So he's still technically in motion. Okay? He's still moving. So for part B, okay, so VFY is what we're looking for. VIY is 0. A sub y is equal to negative 9.8 meters per second squared. And we know the time. Time is 8.8 seconds. So we can use the first equation. VF is equal to VI plus AT. VF is what we're looking for. VI 0 minus 9.8, right? Times time 8.8. So VF is equal to negative 86.3 meters per second y hat. Since they ask for velocity, you need to give the direction. So negative y hat is very appropriate. If they ask, what's the speed of the King Kong before it hits the ground, then you just say 86.3 meters per second. But if they ask for velocity, you better give that negative y hat attached to it. Okay? All right. Next. A foul ball is hit straight up in the air, right? It's a baseball, right? So here's a baseball, and it's hit straight up in the air, right? So the initial velocity of this baseball is equal to 25 meters per second. So it's going to go up, and as it goes up, what's going to happen? It's going to slow down, slow down, slow down, stop instantaneously, and comes back down to where it started. Okay? Therefore, what is the velocity right at the maximum height? Y max? Oh, sorry. There you go. What is the velocity at maximum height? When it reaches the maximum height? What happens when I throw something up in the air? What happens before it comes back down? It stops instantaneously at maximum height, right? Slows down, slows down, slows down, slows down, stops, and then turns around, comes back, speeding up, right? Yes? Therefore, at maximum height, my VFY max is 0. Okay? And baseball, of course, is played on Earth, unless you have your space suit on and then you go play at some other planet. So let's write down everything we know. VIY is 25 meters per second. My VFY max, the maximum height, is 0. My acceleration in y is, on Earth, negative 9.8 meters per second squared. And they're asking how high does the ball go. So they're looking for delta y. Okay. So since I don't have time here, it looks like I can find my delta y using equation number 3. So VFY squared is equal to VIY squared plus 2a delta y. So my VFY is 0. Square that, and you still get 0. VIY is 25. Square that, you get 625. Plus 2 times negative 9.8 times delta y. So 0 is equal to 625 minus 19.6 delta y. So my delta y is equal to negative 625 over negative 19.6, which comes out to 31.9 meters is how high it goes. Okay. Then it asks, how long is it in the air? Well, it's in the air on the way up and on the way down. Does that make sense? So they want to know what the time is for the total trip. Initially, my y initial is 0. And my y final is also 0. So my delta y is 0. Okay? So if we were to look for the total time for part B, my delta y is 0 for the position, for the total trip. Then my VIY is equal to 25. My A sub y is equal to negative 9.8 meters per second squared. And I'm looking for T total. Well, I can use equation number 2, right? I can say delta y is equal to VIY T plus 1 half A y T total squared. So here, my delta y is 0, my VIY is 25 T total plus 1 half times negative 9.8 times T total squared. So 0 is equal to, I could factor out T, so T total times 25 minus 4.9 T total. So T total is equal to either 0 or 25 divided by 4.9. That's 5.1 seconds. So it makes perfect sense. At 0 seconds, it was at 0, y 0. At 5.1 seconds later, it was at 0. Now, some people may say, well, can I just find the time to go from here to here, right? From here to here, and then like double it? And the answer is, yeah, you could do that. You could do that. So you could say, if you want to, like you could say, for let's say B prime, like just so you could say like, we can find delta y is equal to 31.9 meters. VIY is equal to 25 meters per second. AY is equal to negative 9.8 meters per second squared, and T 1/2, right? We can find that, again, using the same equation as this, right? Or if you want to, you can use VF at Y max to be 0. So there are so many ways to do this correctly that, sometimes you could get confused. If I use the first equation, VF is equal to VI plus AT, 0 at maximum height. VIY is 25 minus 9.8 times T. Your T for half a trip is going to equal to 25 divided by 9.8, 2.55 seconds. Double that, and you get 5.1 seconds. Same thing. Okay? Yeah. All right. Cool. Helicopter is ascending vertically with speed of 5.5 meters per second. So we have a helicopter that is ascending vertically at 5.5 meters per second. So V helicopter is equal to 5.5 meters per second. Package inside the helicopter, is also traveling 5.5 meters per second. Does that make sense? I mean, if the helicopter is going and the package is inside the helicopter, it better be going the same speed, right? So this V initial, is also 5.5 meters per second. I don't know why you'd be dropping packages from helicopters, but that's kind of suspicious. I don't know. I don't like it. All right. So here, my V initial for the package is 5.5 meters per second because it is inside the helicopter moving at 5.5 meters per second. It has to have the exact same initial velocity. All right. Well, I also know my delta y is equal to, here is 105 meters initial. And so y initial is 105. Y final is 0. So my delta y is equal to negative 105 meters. All right. Then I know helicopters only fly on Earth so far that we know of. So AY is equal to negative 9.8 meters per second squared. Okay. I'm looking for time. So here, I can use delta y is equal to VIYT plus 1/2 a sub y t squared. Second equation. Delta y, negative 105. VIY, 5.5. T plus 1/2 times negative 9.8 times t squared. So if you work it out, it looks like negative 105 is equal to 5.50 t minus 4.9 t squared. That looks like quadratic equation, right? So if I bring everything to one side and set it equal to 0, I get 4.9 t squared minus 5.5 t minus 105 is equal to 0. So what do you do? Well, you get your calculator out and you could graph this, right? Or if you have it already programmed in there, I think it's a good idea to have it programmed. Or since you're at home, you can just look it up and go look for a quadratic formula. Look at this. Math is fun. How geeky is that? All right. So here, math is fun. You can actually do quadratic equation solver, and then you plug in 4.9. This should be negative 5.5. Whoop. Chair's like falling out of me. 5.5. And C is negative 105. Negative 105. And look at that. I don't even have to press enter. I get two answers. One of the answer being 5.22 seconds, and the other one being negative 4.1 seconds. Obviously, negative time doesn't cut it. So you pick the positive one. I mean, if you pick negative one, if you're correct, you should win a Nobel Prize. I had plenty of negative times during my college years, but they never gave me the Nobel Prize. I still waited. This year, they snubbed me again. Oh well. C'est la vie. So 5.55 seconds is how long it's going to take. Good. All right. Last one. Now I'll let you start your test. This is a good one. Hint, hint. Right. A stone is thrown vertically upwards. Okay. So we're going to throw some rocks, and most likely these rocks are going to be thrown on Earth. So here, stone is thrown with initial velocity of 20 meters per second, and it's going to go up, go up, go up, and it's going to slow down and stop, and then it's going to come back down again. Right? So they're asking how fast is it moving when it reaches 12 meters in height? Most likely it's going to go higher than 12 meters. You could probably figure out how high it gets, actually. But they want to know when it reaches 12 meters, they want to know what the V speed is, right? So what is the V final at 12 meters is what they're looking for. Okay. So what do we know? We know V initial, which is 20 meters per second. We know acceleration in Y, which is negative 9.8 meters per second squared. We know delta Y is equal to 12 meters. So it looks like I don't have a time factor here. So since you don't have time variable, you have to use equation number 3. Very good. So equation number 3 states VFY squared is equal to VIY squared plus 2AY delta Y. So my VFY at 12 meters squared is equal to initial 20 squared plus 2 times negative 9.8 times 12. So your VF y at 12 meters is equal to, right? This is 400. This is 235.2, right? So this is 400 minus 235.2. So it's a square root of, right? 164.8. And when you take a square root of a number, it's always plus or minus, right? So my VFY at 12 meters is equal to plus or minus 12.8 meters per second. So how fast is it going? It's going at 12.8 meters per second. Okay? What about part B? How long is required? What? How long is required to reach this? Yeah, this is what happens when physics major tries to be an English major. No, I think we should say like, how many seconds does it take? Right? Don't you think this sounds better if you say it that way? How many seconds does it take to reach this height? Right? So they're looking for time. Right? They're looking for time when it reaches 12 meters. So for part B, they're looking for t when it reaches 12 meters. We know the initial velocity in y is equal to 20 meters per second, again. We know delta y is equal to 12 meters. We know a sub y is equal to negative 9.8 meters per second squared. Again, it looks like I can use equation number 2, which is delta y is equal to VIYT plus 1/2 a sub yt squared. Here I get 12 is equal to VIY 20 t plus 1/2 negative 9.8 t squared. This looks like quadratic formula again, right? So this looks like negative 4.9, right? So 12 20t minus 4.9t squared. So 4.9t squared minus 20t plus 12 is equal to 0. I just always like to put a as a positive for some reason. So again, we're going to need quadratic formula. So we could go to that Math is Fun site and plug in 4.9 for A, negative 20 for B, right? Well, I lost my mic. So negative 20 for B, and then positive 12 for C, and boom. Wait, I get two positive times here. I get T is equal to 0.73 seconds and 3.35 seconds. Which one's the correct one? Who said both? Why? Yeah, it reaches 12 meters twice on the way up, and then goes beyond 12, stops, comes back down, and then reaches 12 again on the way down, and then hits, right? So they're both correct. So right, 0.73 seconds happens when it is going up, and 3.35 second happens on the way down. So it happens twice, that 12 meters. Yeah. Yeah, same speed, but what about the velocity? Correct. On the way up would be positive, on the way down would be negative. Very good question. Matter of fact, you earned yourself some points for that on your test. Yeah, if you know the difference of that, then you'll get some points on the test. You'll see why. All right. On the test, it won't be on Earth, so I'm just giving you a heads up right now. All right, you're going to have to calculate the acceleration due to gravity on this planet that you have no idea where it is. And then you have to use that calculated acceleration due to gravity for the rest of the problem. All right, any questions from any sides? I'm going to stop the recording here.